Welcome to Learning to Engineer. In this video, we are going to be talking about the V2I converter using Opamp. This circuit is mainly used in the testing of the semiconductor devices like diodes, LEDs, zener diodes, and many other applications which is related to the testing of the device. Let's get started. We are going to use the Opamp IC in negative feedback now. We will be using a small input resistance which is generally in the order of 100 ohm or something for this circuit. For now, let us call this as Rn. Okay, and in the feedback path, we will have a resistance which is Rf, and this resistance will be replaced by our testing device in the future. We are going to be discussing more about that in the second half of the video, but before that, let me first explain you how the circuit works. This is based on a very simple principle actually. In the non-inverting terminal, we will be applying our signal input, which is Vin, which is approximately like 1 or 2 volts in the range. And obviously we will be supplying this with plus VCC and minus VEE for the operation of this amplifier. Okay, so if you want to know the basics of this, you can quickly check out this video where I have explained a lot about how this op-amp works and the differential mode of operation with BJTs. Okay, so now V2I converter. Okay, by virtual ground concept, this voltage will be Vn, right? So when we are applying the Kirchhoff's current law, the current that is entering this 100 ohm or this input resistance will be same as the current that's flowing into this output resistance. So let's apply Kirchhoff's current law now. By the Kirchhoff's current law, what we are getting is 0 minus Vn divided by 100. Okay, it's not 100 for now, this is Rn. Okay, but divided by Rn plus Vin minus Vout divided by Rf is equal to 0. So we are going to rearrange these terms for now. So Vin by Rn is equal to Vin minus Vout divided by Rf. So let's rearrange the term and find out Vout. So we are going to have the value of Vout in one side, Vout by Rf in one side, and then we will shift this here. So this will be Vn into 1 by Rn minus 1 by Rf. Okay, so I'm also taking Rf to the other side now. So this will be Vn into, I'm multiplying Rf in the both terms. So this will be Rf by Rn minus 1. This is equal to minus Vout. So what is plus Vout? We will just like exchange these terms. So Vout will be Vn into 1 plus Rf by Rn, which is pretty much the definition of non-inverting configuration of amplifier, right? So this is what is the output voltage in this configuration. Whatever be the input that we are applying here, if this is maintained as a constant value, we will be getting a constant value of current in the feedback path. This current will help us determine the healthiness of the device that is connected in the feedback. So to test whether two diodes are matched, what we will do is, we will be removing this feedback resistor and connect the diode like this. Okay, so we will remove the feedback resistor and place the diode in the feedback path to test the voltage across this diode, because across it you will be getting the value of Vin divided by Rn in this path, right? Because this current is going to flow into this, which is nothing but Vin by Rn. So this current is measured by Vin divided by Rn, and when you are passing a constant current, what is the current that this diode allows and what is the drop across it? This will be measured for, let us say, diode 1. Now I am going to remove this yellow diode, which is D1, and I am going to replace this with, let us say, blue diode. or this is another diode. Okay, so for this diode D2, what is the value of the current that it passes, which is going to be same because it is set by Vn and Rn, and for a constant amount of current, what is the drop across this diode? If the drop across this is, let us say, V2, and the drop across the previous yellow diode is, say, let us say V1, if both are same, then we know that both these diodes are identical and they can be matched. Okay, so test the matching of the diodes, this circuit is used. There is also another application using this, which is the testing of the breakdown voltage of the zener diode. Let us say in the manufacturer's specification, you just got the name plate worn out, or you do not know the breakdown voltage of that diode. You don't even know the model of it, and you are not able to find that in the data sheet. In that case, what will happen? You can use this circuit to find out the breakdown voltage of that zener diode. It is the same principle. You will be removing the feedback resistor. You can connect a zener diode across it like this. Okay, in the feedback path, if you connect the zener diode, the knee current of it will be very less. Let us say in the order of 1 or 2 milliamps only. So when the knee current is made larger than the allowable knee current of this diode, I have said you that you have forgot the model number, or you are not able to access the data sheet in that cases. Okay, so you can set the value of this current greater than the knee current of the diode, such that this diode operates in breakdown. So the voltage across it will be the voltage of the breakdown voltage of this diode. Okay, so you are purposefully setting this current, which is Vin divided by Rn, to be greater than the knee current of the greater than the knee current of the zener diode. Okay, so when you are setting this current such that it is greater than the knee current of the diode will be in breakdown, and the drop across this will be the breakdown voltage of this zener diode. I'll also tell you a third application. Okay, in the feedback path, I can also connect a LED light to test whether the brightness of this light and some other light is matched. When you are using LEDs in some panels or in light panels or something, you will be using an array of LEDs together, and you want all of that to be of the same brightness. If one LED is so bright and the other one is not, you cannot just fit it in the panel. Imagine a railway station panel which uses LED, and each of these LEDs is of different brightness. It will be very difficult to see the board. So you must have that board with same LEDs with same brightness. How to test that? It's simple. I mean, you can also do that by other methods, but this is one of the methods. You can simply connect the LED like this. Okay, be sure that the P junction is on the output side, because the feedback current will be like this normally. Even though for conventional purposes we take the current direction to be like this, the feedback current is actually from output to input, not from input to output. Just for our easy calculation we are doing that, which is not wrong, because the voltages I am considering it to be the same. So basically the feedback current path is from output to the input. So this current direction is like this. So the P junction should be on the output side, and the N junction of the LED should be in the input side. Okay, so in this LED, if it gets illuminated by some level of brightness, you can just note down you can just measure the brightness, save it aside, then you can replace this by another LED. Okay, so what I'm doing is I'm just replacing it by a yellow LED. Okay, so now I am replacing it by another LED and checking the brightness if the brightness is same, because the core principle behind all these applications is that the current through it is set by Vn divided by Rn, which is the external guys. So when we are sending a constant current, how much is the brightness of one LED? You replace that with another LED. What is the brightness? Whether this brightness is same as this, you are going to test that with the help of the voltage to current converter. So in this video we have seen how the voltage to current converter works and the applications of it. So there is a small error when you consider the practical aspects of this. which is the offset null concept. We will look at that too. So when you are having a feedback resistor, there is a concept called input offset voltage, which we saw in this video. So because of this input offset voltage, there will be errors in the circuit when you don't have any input applied to it. When you do not have any input, Vin is 0, even then you will get an output in this end because of the plus and minus VEE. So we are correcting that by means of a resistor which is connected like this. Okay, it is connected across the input and the output terminals, and the adjustment value will be based on the VEE. Okay, so at what value of this position you get 0 output, at that position you have to keep. Let us note this as small r. This resistance is called a small r, and this resistance is used the offset null voltage. So because when you are adjusting the value of this resistor, at what value of this resistance you are getting the output voltage to be 0. This is the null offset resistance. Just note down that resistance and then you are good to go. You can use this in any application. You can replace this feedback resistor by any PN diode, or you can just replace this by zener diode, or you can even replace this by LEDs, and you can use it in different configurations. Thanks for watching. If you have any questions, you can let me know in the comment section, or you can email to learningtoengineer@gmail.com. Thank you.